Differential equations, type 2, real world, D, nonlinear motion. So 2012 is where we first saw these nonlinear motion questions appearing because of the change in the Project Maths course. So this was a nice slow introduction because again it was giving us the equation to us. So we didn't have to try and figure out how to set up the rate of change. So here we were told that Newton's law of cooling states that the rate of cooling of a body is proportional to the difference between the temperature of the body and the temperature of its surroundings. And theta is the difference between the temperature of the body and the temperature of the surroundings. Then d theta dt is equal to minus k theta. So again, the negative sign here because obviously it is cooling. So we're told that a body cools from 80 to 60 degrees in 10 minutes, and the temperature of the surroundings is maintained at 20 degrees Celsius. And the first thing we have to do is find the value of k. So what is this constant of proportionality? So let's see what we have at the start. So we have d theta dt is equal to minus k theta. And our start limits and our end limits are given to us as theta. Well, at the start it's 80 and it cools to 60. In other words, the change in temperature is going to be 20. Sorry, no, that's not. It's 80 minus the temperature of the surroundings. So the surroundings is 20 degrees. So that's 80 minus the surrounding temperature is 20. And therefore the change there is 60 degrees. And the temperature at the start is, the time at the start, I should say, sorry, is 0 minutes. At the end, the final temperature is 60, so with respect to the surrounding temperatures, which is always maintained at a fixed rate of 20 degrees Celsius, then our theta value is 40 degrees, and that's after 10 minutes. Okay, so let's have a look then at our equation. So we're going to rearrange that. So we're going to have 1 over theta d theta is equal to minus k dt. If I put in my limits, I have 1 over theta d theta is equal to minus k dt. Upper limits are my end limits, and lower limits, sorry, this should be 40, and lower limits are my start limits, which is 0. Okay, so if I'm integrating 1 over theta with respect to theta, well then that's a linear, 1 over a linear function, and 1 over a linear function when we integrate is natural log. So we have natural log of theta between the limits of 40 and 60 is equal to minus k t within the limits of 10 and 0. So if I sub that into my equation, that is our upper limits minus our lower limits is equal to minus 10k. And of course, if I get k on its own then, and we're using our log rules, page 21 of our maths tables, or sub it straight into your calculator, that's up to yourself. So you're going to have a natural log of 60 over 40 divided by 10, which gives us a value of 0.0405. Okay, so if I go back to the question, it just says find the value of. So generally when it says find the value of, that would be expecting you to find your decimal place answer. Now it's not saying to how many correct decimal places or anything like that, but we were given 15 marks for this question. So we had 5 for setting up, 5 for integrating correctly, and 5 for getting our value of k. So part 2 then says find the temperature of the body after a further 15 minutes. So let's see what we have here then at the start and at the end. So at the start, our temperature is maintained, as we saw there. It's a further 15 minutes. So therefore it ended at 40 degrees. So that means it's now taking it from that point on, which is 40 degrees. And the time, we're taking that to be our start point. And then at the end, well, what is the temperature going to be? Well, we don't know, but we know that theta is the difference between the temperature and the surroundings. So it has to be theta minus the fixed temperature of 20 degrees. And the time is 15 minutes later. So 15 minutes after that initial start point. Okay, so again, if we look at our equation, well, it's 1 over theta d theta. This time our upper limit is theta minus 20 and our lower limit is 40. And that equals minus k dt, with our upper limit is 15 and our lower limit is 0. You can, of course, sub in for k now, or you can sub in for k in a minute. That's up to yourself. Because it's a big decimal there, I'm just going to keep it as k for the moment, and then I'll sub in for k once I've integrated. That's totally your personal choice, okay? So just don't forget to sub in for k, because we know what its value is. So if I integrate 1 over theta, again, linear, so natural log once I integrate. Okay, and now if I sub in my values, and I sub in my value for k, I'm going to have natural log of theta minus 20 minus natural log of 40 is equal to minus 15k, but we have to say k is equal to 0.0405. And again, subtracting my logs, which means I'm going to apply the same rule where I divide. And that's minus 15 times 0.0405. And now if I simplify that, well, what do I have? I have natural log of theta minus 20 over 40 is equal to minus 0.6075. My log rules, page 21, top right hand corner. Again, converting from log back to indices. Well, what have I got? Well, it says if I have log y to the base a equals x, then that's a to the x equals ry. Okay, and therefore that can be written as theta minus 20 over 40 is equal to e to the power of minus 0.6075. And I want to get theta on its own, so I'm going to multiply both sides across by 40 and then add 20. And therefore that gives me theta to be approximately 41.8, and was units given to us in the question, it was, so it's degrees Celsius. Okay, and there was 5 marks again for setting up and integrating, and 5 marks for getting it out totally right, and therefore that was 25 marks. So a nice question. Once you've seen a few of these non-linear ones, they become very, very nice. Okay.